In this video, I will show how you can utilize DIC or digital image correlation analysis on tensile test within 10 or 20 minutes without any additional equipment for free and with very high quality. To include DIC in your tensile test, you will need a mobile with good camera, the material to test, and spray paint. It could be acrylic like this if it is metal, or chalk spray paint, which I will use in my case as my material is thin and flexible. You can purchase these paints as low as just $1 from online, or you can buy them directly from the paint shop. The specimens here are created by cutting these polymer films. I have now put the specimen on a flat surface and used a long press on the paint can to have random sparkle pattern. This was good enough for me. The test specimen is now mounted on the tensile test machine. I used a custom made mobile holder to record the video. Adjust the focus of the video directly on the specimen. You can use any other way to hold the mobile. This is the welcome screen after opening GOM Correlate. This is a free software if you want to do two-dimensional correlation. I will leave a web link in the description of the video, and then you can click that link, download and install GOM Correlate in your computer. Create a new project from here or from File, New Project. Let's create it from here. I can import the test video that I recorded using my mobile camera by going to File, Import Files, and finding the right file location and import it from that folder. Or I can open that folder containing the video. So I have the folder containing the test video in my secondary monitor. I will drag that video and drop anywhere in this window. As I have a 180 megabyte video, it will take some time to load. The video is now loaded. It took me about 4 minutes to complete loading, but if your video size is less than what I have, it will take shorter time to load the video. Now I can see there is a timeline that appears at the bottom. There is a white box. This is diagram. Right now we don't have any diagram. The diagram is now maximized. If I click on diagram again, it will minimize. Right now, I don't want this window, so let's minimize that. I have recorded this video using a iPhone 11 and it records 30 frames per second. So I have this timeline for 85 seconds. Every second, I have 30 images. So if I right click in this timeline and select Manage Stages, I will see that the number of stages a bit more than 2500, and that ends at 85.6 seconds. Let's click Close, and now let's go along with the timeline once more and see what happens. I will now hold this red line and slide in the timeline, and as I can see towards the beginning there were no deformation. That means I started to record the video, but I did not start my tensile test machine to induce deformation. And I can see this is 108, 120, 123, still no deformation. Around at this stage, after 172, the deformation starts. So I will disable all the stages up to 171. To do that, right click and then Manage Stages, and to disable from 1 to 171, click the first stage, scroll down and find 171, and before clicking that, press the Shift button in your keyboard and then click 171. And by that, from 1 to 171 stages are now selected. I will right click here and say Disable Stage. You can also delete stage. Click Close. Although I have disabled about 171 stages, I still have 2563 stages. So if I right click in this timeline and select Manage Stages, if I want to analyze all these stages, it will take me probably an hour to do the correlation. A good trick is select anywhere and then Control A such that all those steps are selected. Then here you will find thin enable stages. Either you go from here or right click, you will also find thin enable stages. I will select to use every 20th stage. And as I do that, the stages in between are disabled. And after this, for example, this particular stage, next 19 images from the video will not be used in the correlation. Instead, the 20th image will be used just after that. If for with all the stages it would take 1 hour, right now it will take only 3 minutes or less. Sometimes it is necessary because we cannot reduce the frame rate in our video, but then we can thin as we want. If we have our frame rate too much, we can thin a bit more. If the frame rate is less, maybe we can thin it by every 5th or every 10th stage. But we are happy now. Click close. I would also like to indicate that at the end of this loading, when I stop the test, it unloads. We can also delete those stages right now, or I will show you that after the analysis of DIC is complete, you can also delete them later. So I will keep these stages right now and demonstrate that one later. Let's go back to the undeformed stage. And I know from here to here, distance between the grips are 100 millimeter. So I want GOM correlate to know that. For that, I will go to actual element, right click and edit creation parameter. And in the pop-up, I can go edit calibration and define scale. And then it will ask you to define a point in x-axis. So point 1 in x-axis or the beginning point of x-axis, and point 2 in x-axis is the end point of x-axis. This is our x-axis, so I will define that from here to here is 100 millimeter. So I will now press the control button in my keyboard and click here, and then again keep pressing the control button in the keyboard. I will click here. So this line or this distance is now showing by default 100 millimeter. If this is not the case, change that number and click OK. And then also click OK here. Now we will define surface component. This is something that will divide this whole domain into small squares, and it will also have some overlapping squares. And as this specimen moves, those squares will move, and from those movement it will calculate the displacement field, and from that strain field and every other output that you request. So to define those surface component, we will go to define component, surface component, and here in this pop-up says facet size is 18. That means each square is approximately 18 pixel. These are not to the scale. Actually, they are much smaller for being 18 pixel. And then point distance is 12. That means center point of one square to another is 12 pixel. So this square comes in pair, and this is to help with the computation. Now what you need to know is what facet size you would use, because you can reduce or increase them. 18 and 12 is very good value, serves many cases. But as a rule of thumb, if this stochastic pattern is very fine, then you would like to have both this facet and point distance smaller. For example, you can reduce it to 9 pixel and reduce this one to 6 pixel if these patterns are much finer. But for my application here, I think this is good. You can also see this facet size is 1.5 times of this point distance. If you want, you can keep the same ratio when you change the facet size. This usually gives good accuracy. And in computation, you can go for high accuracy or more points. You are encouraged to use high accuracy. There are some expert parameters. You can keep them default. While this create surface component window is open, we'll also select which area we are interested to do the DIC analysis. To do that, we will select this select deselect polygon, click here, and then we can start clicking on the screen. So I will click first here, then here, and here, and finally I will click here. So that covers my whole specimen. And after this fourth click, I will do a right click, and there are two options. This one is create and this one is create and close. So if you don't want to change anything in this window, you can just select create and close. It will take some time to do the analysis, and I can see that all the images are now analyzed. You have probably noticed that I have selected towards the boundary line. It is not always necessary. It's usually safer that if you select a point here, here, one here, and one here, keeping some clearance. Now, as the analysis is complete, and surprisingly, it took only maybe 10 seconds to do the analysis. But if you have more frames or more stages, like in our case, we had only 125. If you had like several thousand, the required time for computation increases exponentially. So let's go ahead and see some of the results. And to check the results, we will go to this tab, all visible actual elements. And from here, you can select the strain in x-axis, in y, or major strain, minor strain, these are the principal strain, or displacements, and so on. So as we can see, the x-axis is along here, so you will see what are the strains epsilon x along the x-axis. So click here, and there is a default name, accept all the defaults and click OK, and within seconds the analysis is complete. Right now we can see the color coded strains and the value are given by this legend. So let's go along this timeline. I am clicking in this red line and pulling it. So as I go along the timeline, it shows the strain distribution. So this is a full field strain measurement, and I can see that the strain color is around these probably. So the strains are 0.16 or 7. But if we really want to inspect and see the values, we have to use other tricks. But before that, let's go ahead and see what are the strains in y-axis, the epsilon y. So click epsilon y, click OK. Now we can see the strains in the y-axis, and we expect this strain to be negative, and we can see the value here is negative indeed. So as we go forward, you can see that the compression that is felt here, the maximum is minus 0.576. So it is quite much compressed here, but maybe we are interested somewhere here and see what the value there. But for further analysis, let's go to epsilon x, see the strain in this direction. The simplest of inspection is if we click here, we can do point inspection. So click here. Now it is possible to select anywhere and a point will appear. So I will press Ctrl in my keyboard and click somewhere in the middle. So it says point 1. Now I will click escape. So point 1 is now visible. If I go into actual element and geometries, I see points, and inside I have point 1. So we know the location of point 1 here, so that if needed we can delete these points. But right now, to see the result at that point, we have to go and click epsilon x again, because last time we did that the point was not there. So anything or any geometry that we add later, for that we have to run this surface component once more. So just click here and accept everything. And now the strains, and now the strain in x-axis has been computed at that point. So how can you see them? To see them, you can go to diagram. It will show this timeline, time in x-axis, and true strain in the y-axis. And this line shows where I am, and this red line actually indicates this red line. When the strain distribution is this, then at this particular point I have strain of point, you can see in the y-axis 0.075. So let's click here and minimize that, and let's put another point somewhere here, because the local strain at that point and local strain at that point should not be the same. So let's go ahead and point inspection, press Ctrl in the keyboard and click here, and then escape in the keyboard. Then I have 2 points. I can see point 1, point 2. As this point was added later, we will do the same analysis again. Click here. Now in diagram, I should have 2 figures. The first figure shows the strains at point 1 as a function of time. Now, as there are 2 points, we can see this is point 2, this is point 1, or we can click here to show the legends. The black curve is for point 1 and the blue curve is for point 2. If we don't want to see any of the curves, we can click in this I sign. The strain as a function of time for point 2 will not be visible in this diagram. Now, if I want to have this time versus strain, I can do that by clicking export diagram content, and then it will say that at that folder, this file will be saved by this particular name. I can click here and change the name and as well as folder, but let's keep the default and click OK. I will now open and show you the file where it was saved. So I have opened that file. By default, it opened in Microsoft Excel, and I can see there are 2 columns. In the first column is time, and in the second column is the true strain at point 1. Let's click in diagram and hide it and see what else we can do. If we want, we can select equidistance points. So by clicking here, it will create multiple points at equal distance. We can create section view. So for example, I will show you what it is. If I click here, it will ask me to select 2 points of section. I will select 1 point here and create the section. This time I don't need to press Ctrl or anything. I can just click here, go up, left click here, and I have this section. Create, close. Now the new section is created. Let's say I want to see what is the strain distribution in X direction in this section. It might not be constant. The strains in X direction might be different along this cross section. But again, as this cross section was created after we selected epsilon X, we have to click it again and accept. OK. Now the strain distribution along this section should be available in diagram. But we can see we have only the point time versus true strain diagram. Let's hide that. And we have the strain in the section. But instead we hide that and click here. We have strain in point 1. We have strain in point 2. But we hide all of them or just select that. We will have the strain in this cross section. If you look carefully in the x-axis this time, we have length. We don't have time. In y-axis, we have the strain. So length is from here to here, from here to here. This is about 18 millimeter. And the strain is the strain values. As this is at a given time, this curve will change as we move along the time, and the curve is changing. And we would see that along this curve at this given time or given displacement, the strain is not a constant straight line. It fluctuates as minimum of 0.1835, maximum of 0.1849. It's not much, but it is there, some deviation. If we want, we can again export, but if we do that, we have to remember that we will get the strain as a function of this length only at a given time where I ask this curved at. If you don't want to get confused by so many curves and what you have selected and what not, you can delete whatever you don't need. For example, right now I am interested only to look into this section strain. I am not interested in these points. So I can right click in these points and say delete. I can say delete anyone or both together in this main menu points. So delete element. And of course, I don't have anything else. I have only one curve. Let's minimize that. And the final thing in this video I will share is how to use virtual extensometers. We can do that by going to construct and then distance, and then finally we will find extensometer. Click here. We can keep the name as default, and then it asks for a distance. That means in which direction. So I will draw an extensometer somewhere from here till here. So this is definitely x-axis. So click X. This is plus X, means if I select the first point here, the second point will appear somewhere there. And the length of this extensometer, I want 10, and that's actually it. So I will again press Ctrl in my keyboard and left click here. And I can see this is almost what I want, about 5 millimeter there and 5 millimeter there. If I think this is the center line, and if this is what I wanted, I will accept and close, and this will close these as well as this window. So with extensometers, we will ask for length change. So that means if it is 10 millimeter at the beginning, how much the length has changed in X direction of this extensometer line. So click length change, accept default, OK. And again, now if I go to diagram, as I have this section and the extensometer can be found in these facet points. So extensometer point 1 and extensometer point 2, point 1 and point 2. So in diagram, there could be confusion. So let's first say I don't want to see the section results. Now if I go to diagram, for this extensometer, we can see the length change in percentage as a function of time. So this extensometer gives me at any given time. So this curve is available for me to know what was the change in length in percentage. Usually the percentage of change, if I divide it by 100, that will give me engineering strain. I can again export these results or these points in the curve. If sometimes you think that there are localization at very high strain, to capture that local strain, we can place small strain gauges. This time we use 10 millimeter. We can even use 1 millimeter, 2 millimeter at the place where in the video we see there is a necking or there is a failure. If this is the failure line, we can place a very small extensometer, 2 millimeter, that is one point of the extensometer here, and another one is there. And by doing that, we will get to know the engineering strain from this length change locally where necking is occurring. So for the next video that I will demonstrate how you can use this extensometer to capture the true stress strain by combining the strain measurements from GOM correlate together with the force response from your tensile test machine. I will save this data, and I will save this one by a name of extensometer strain response. I was not being able to save it because I had this cross-sectional curve interfering. So I just from here deleted the cross-section and name it extensometer X direction and click OK.